Good day, ladies and gentlemen. Welcome to the first lecture of Digital Electronics 2, which is CMEN405. And this is a course that is supposed to be continuation of Digital Electronics 1, which is CMEN307, and it is going to be taken by me, Engineer K. Abubilal, PhD. And without waste of time, we go straight to the first item on this our course, and this is nothing but the residual knowledge that is expected from any student that is taking this course. You are expected to pass 307 before you are allowed to register this course, and these are the things that you are expected to remember. The first one, you are expected to remember your basic logic gates, remember their truth table and the Boolean equations, that is the Boolean function of all the logic gates you have seen in 307. You are also expected to be able to remember the fundamentals of Boolean algebraic simplifications, and also you are expected to remember how we use Carnot map for simplification of Boolean functions. So with this, the first thing that is expected to be taught in this course is presentation of the general block diagram of basic digital computer. And if you look at this diagram, we can see that any digital computer basically have a processor, it has a control unit, it has a storage or memory unit, and input devices and the output devices. So why are we treating or presenting this block diagram in this course? The reason is simply because we want to tell the students that this processor, the control unit, the storage unit, and the rest, they are all designed and fabricated using the general knowledge of digital electronics. Therefore, the things we are going to do see in this course, they are basically like the basis from which any digital system, including digital computers, are designed from. And the first thing here is we are going to look at the design and operation of the logic gates. Of course, we know from our knowledge of 307 that the basic logic gates we have include AND gates, OR gates, the NOT gate, which is an inverter, the NAND gate, the NOR gate, and the rest like exclusive OR, exclusive NOR, and many more. Now, these gates, they are fabricated using discrete components, and the discrete components include transistors, diodes, resistors, and the most, that is metal oxide semiconductor devices. So based on this, we have different categories of the logic gates depending on which components are used for fabricating them. The first one is called resistor transistor logic, which is RTL. The second one is diode transistor logic, DTL. The next one is transistor transistor logic, which is TTL. And we have metal oxide semiconductor logic, which is MOS. Now let us start with the first one, which is resistor transistor logic. This is a family of logic gates where the basic discrete components that are used for fabricating the gates are resistors and transistors. Of course, you can see other components in the circuit, but the main ones that are used for the switching operation, they are resistors and transistors. And of course, this RTL logic can be used to fabricate any type of logic gates. But for the sake of illustration, we are going to look at the NAND gate version of this RTL family. And this is the typical circuit diagram. If you look at it, we have our supply VCC, and we have a resistor R here. Its function is to limit the amount of current coming to this transistor. And of course, we have our two inputs A and B. Each of them is delivered to the base of the transistor through current limiting resistor. And in this logic, there are some points we need to understand. First of all, any voltage that is at the level of 0.2 downwards is taken as logic low, that is as 0, and any voltage between 1 volt to 3.6 is taken as the logic high, which is 1. And if we want to analyze this circuit, we first of all assume that since we have two inputs A and B, this is the truth table, and we know for two variables the combinations are 0 0 0 1 1 0 and 1 1. Now let us start with the case number 1, where A is 0 and B is 0. Now if these two are 0, it means there is no base current going to transistors T1 and T2, and for this T1 and T2 are not conducting. Therefore whatever comes from BCC does not have a way to ground. Therefore the value of this BCC will be detected at this point. Therefore my F in that case will be high 1. And looking at the second case, A is low but B is high. The fact that A is low, it means transistor T1 is not conducting, so what comes from BCC will remain here. F will also be high. And the next case is where we have A is high but B is low. So if A is high, it means transistor T1 is conducting. What we have here has a path to the emitter, but when it reaches here, it cannot go to ground because B is low, which means transistor T2 is not conducting. So at the same time, this voltage cannot go to ground, so my F will also be high. But if you take the last case where A is 1 and B is 1, meaning they are high, so transistor T1 and T2 are conducting. Therefore there is a path between the collector and emitter of T1, and also there is path between collector and emitter of T2. So whatever we have here can go up to the ground. Therefore our F should be low because the voltage here drained to the ground, so the output should be low. Now if you look at this, where any other combination gives 1 except where we have 1 1, it means it is what? An inverse of AND gate, because for AND gate it is only when both of them are 1 1 that we get 1 as our output, but this one is its direct opposite, which means this gate is an AND gate. Now if we understand this one, we go to the next class of this logic gates, which is diode transistor logic. And this one, as the name implies, it is fabricated using diodes and transistors. Of course we can have other components, but they are not the major concern, and we can use this DTL logic to develop any type of logic gates, but here we are going to illustrate its operation using NAND gates. Now in this case also, a voltage of 0.2 is taken as low, and anything from 4 to 5 volts is taken as logic high. Now my VCC is supposed to be between this 4 and 5, and you know it will come here, and at the same time it will come here, the same value, because they are in parallel. Now if any one of these input, either A or B or C, is not conducting, it is low, it means whatever comes from here can pass through that diode and go out. So, and we should remember that these diodes, they are expected to be a silicon type diodes. Therefore they have the minimum voltage for them to conduct, that is turn in voltage or turn on voltage, which is 0.7. Now when either A or B or C or more than one or all of them are low, it means what comes here can exactly go to the ground. And in that case, the only thing we can have at this point is that drop across the diode, which is 0.7, and the low voltage, which we said is 0.2. So meaning the total voltage you can find at your point P is supposed to be 0.9 volts. But this diode requires 0.7 to conduct. This one also requires 0.7 to conduct. Then between the base and the emitter of this transistor is also another PN junction diode. Therefore you need 0.7, 0.7 and another 0.7, making it 2.1 minimum voltage for this transistor to start conducting. But we have seen that whenever either A or B or C or 2 or all of them are low, the maximum voltage we can have here is the drop across the diode, which is 0.7, plus the low voltage applied here, which is 0.2. So here we have 0.9. So in a situation where any one of them or all of them are low, the maximum voltage at P is 0.9, but for this one to conduct requires 0.7 plus 0.7 plus another 0.7, which is 2.1. So in that case, this transistor is not conducting. If it is not conducting, what comes from BCC remains here, which means my Y should be high. Okay, but now in a situation where A, B and C, all of them are high, so if like 4 volts comes here or 4.5 volts, and also these ones, they are at that same voltage, 5 volt or 4, so it means the potential difference between each of these diodes should be 0, which means the diodes are not conducting. So if they are not conducting, the voltage that comes from BCC will be present at this point P, and we said it should be either 4 or 5. Now whatever the value is, it is more than the required 2.1 to make this one conduct, and transistor to conduct. So in that situation, our Q1 is conducting, so whatever comes from here can go to the ground, which means the output should be low. So if you look at this one, we can see that this is an example of a NAND gate, because only when all of them are high that we get low, but in any other combination we have high. So the next one is transistor logic, TTL. And if you look at this one, it is just like replacement of this. Instead of using these diodes, we are using transistors in their place. And if you look at this, we have PNP, a transistor Q1, but it has multiple emitters. And we remember that between the base and the emitter of any transistor, we have a PN junction diode. So therefore, between this base and the emitter number 1 is PN junction diode 1, and between this base and the second emitter another PN junction, between the base and this emitter another PN junction. Therefore, these 3 emitters and the base give us the 3 diodes we have here. And then between the same base and the collector is a PN junction diode, which is standing for this D1. And if you come to the second transistor, between the base and the emitter we have another diode, which is standing for diode D2. And finally, this transistor Q3 is working as my active transistor Q1 here. So if you understand this, the procedure, the operation of this one and this are all the same. This is also a NAND gate. Now we go to the next item, which is the metal oxide semiconductor gates. This is another way of fabricating digital logic gates, and it has an advantage of the fact that you can fabricate many gates, many devices in a very small area of your metal oxide semiconductor, because the same gate can also be used as current limiting resistor, and we can use this one to fabricate any type of gate. But for the sake of illustration, we illustrated how to fabricate inverter, NOT gate, NAND gate, and the NOR gate. Now we start with the inverter, and for us to understand it, we look at the logic diagram given here. If you look at it, we have 2 metal oxide semiconductor transistors, this Q1 and Q2. But if you look at the first one, the gate is always connected to our source, which means this transistor is always in conduction state. For this, it is used as the current limiting resistor. The active transistor is Q2, which is regulating the switching. And how does it work? If our A is low, that is our input is low, it means the gate of this MOSFET is low, and therefore this one is not conducting. So if it is not conducting, the voltage that comes here cannot go to ground, therefore my output should be high. But when A is high, it means Q2 is conducting. Whatever we have here can go to ground, and therefore my output should be low. That is why we now say Y is equal to A prime, meaning if A is high, the Y should be low, and if A is low, the Y should be high. Now the second example of this MOS family is the NAND gate, and it is fabricated like this. The first gate is used as current limiting resistor, and Q2 and Q3 are our active transistors. Now let us start with the condition that both A and B are low. If they are low, it means Q2 and Q3 are not conducting. What we have here cannot go to ground, our output should be high. But when A is low, B is high, Q2 is not conducting, no way to ground, therefore here should be high. If A is high but B is low, still there is no way to ground because this Q3 is not conducting, still my Y should be high. But in a situation where A is high, B is high, it means Q2 and Q3 are all conducting, therefore whatever I have at this point can directly go to ground, therefore my Y should be low. So if you look at this one, whenever both of them are high, the output is low, but any other combination, the output is high, and this is exactly the operation of NAND gate. Another example of this MOS gate is the NOR, and it is fabricated using this logic diagram. This Q1, as usual, it is always in conduction state, and it is used as current limiting resistor. Then my Q2 and Q3 are the active components, and now let us assume A and B are all low. So if A and B are low, it means Q2 and Q3 are not conducting, therefore there is no way to ground, there is no way to ground this way, therefore my Y should be high. But when A is conducting, B is not conducting, we have a path here so that it can go to ground, the output here should be low. And if A is not conducting, if B is conducting, there is another path here through Q3, and therefore the output should be low. And also when all of them are conducting, there are two paths, everything should go to ground, and Y should be low. So looking at this one, we can say that this one is a NOR gate, because whenever at least one of them is high, the output should be low. It is only when both of them are low that we have high here, and that is exactly the function or the nature of NOR gates. Now after looking at these families of the logic gates, we look at the integrated circuit in which these logic gates are fabricated. And for your information, these gates are not fabricated as discrete component, like if you want to buy an AND gate, you go and buy it. No, you have to buy an integrated circuit in which you have the number of gates. This is a typical example. Whichever IC you have that is dual inline package, meaning it has pins on this side and pins on the other side, it is called dual inline package deal. And if it has this number 7408, it is AND gate, and the AND gate inside they have two inputs, one output. And if you look at the internal structure of the gates of the IC, we have 4 of these gates. You can have some numbers added in front of this 7408 or after it, but once this one remains the same, the IC remains the same. It contains 2 inputs, AND gates, and there are 4 of them. But any other one has its own nature. If you check the notes, they are all there. I have given examples of them. Now after looking at this, we now come and look at the special properties of the logic gates. That is, whenever you want to buy a logic gate to use it for a particular operation or application, you need to know these properties so that you can select the one that is suitable for your application. The property number 1 is called fan out, and this fan out of a gate is nothing but the number of other gates it can drive properly without being overloaded. So let us illustrate this by assuming this is our gate number 1 and it is producing an output. The output of this gate is now used for driving other gates, that is, it is serving as input to other gates. So the fan out of this gate number 1 is how many of these gates can each pitch without being overloaded. And how do we calculate that? All we need to know is to know what is the amount of current that this gate can produce when it is in logic high, that is high output here, and what is the current requirement for these subsequent gates it is driving when they are in high state. Supposing I have this one produce like 100 milliamp and each of this one requires like 10 milliamp. Now the fan out is equal to the current produced by this gate all over the current input required by these connected gates. And if we take our example, here is 100, here is 10, 100 over 10 will give you 10. It means gate number 1 can drive 10 other gates without being overloaded, and that is what we call the fan out of this gate number 1. Now we go to the second property, which is fan in. And the fan in of a gate is just like opposite of the fan out. It is the number of other gates, that is the output of other gates it can accept now without being overloaded. If you look at this, supposing this is my gate number 1 and its input is now connected to the output of multiple gates starting from number 2, 3 up to the end. So the fan in of gate number 1 is how many of these gates can be connected to its input so that it can operate properly without being overloaded. And if we want to do that, we use the same formula we use for the fan out, only that here we have this input current all over the output current. What I'm saying is that supposing this gate can accept up to 50 amps and each of these gates that are connected to its input are producing like 5 milliamps, 50 milliamps, and here they are producing 5. Now if you say 50 all over 5, it will give you 10. It means 10 of these gates can be connected to the input of gate 1 without overloading it, and this is what we call the fan in of that gate. Then the property number 3 is the power dissipation, and this power dissipation is nothing but the amount of power required by the logic gate for it to operate. And for us to determine that, all we need to do first of all is to get the amount of voltage that is used for driving the gates, that is the supply voltage, VCC. And now we find the current, but of course we don't have only one current, because the current it is absorbing when it is in high state is different from that when it is in low state. So for us to get the current requirement, we need to get the average of the two, that is the current when it is in high plus when it is in low, and divide by 2. Whatever you get is your average current requirement. Now the power should be the product of the voltage and the current, and this is what we call the power dissipation of a gate. Property number 4 is called propagation delay, and this propagation delay is nothing but the average transition delay, that is average time it will take the signal to enter the gate and appear at the output of the gate. So the time it will take between entering and coming out is called the propagation delay. Of course, we don't expect that immediately when the signal enters the gate it comes out. No, there's some delay. But that delay, if you say it to a layman, he can laugh at you. You say like 1 microsecond or 10 microsecond, that is 1 second divided by 1 million. Even 1 second itself is very small. What of dividing it by a million? But for electrical engineers, that is very significant and it has effects. And for us to illustrate this propagation delay, let us assume that this is our signal that is being delivered to the input of the gates. and this is the one that is coming out after it enters the gate. So if you look at this, this is where the input signal started rising from low to high, and the one that is coming out will start rising from this point. And if you compare the starting point of the input and the starting point of the output while rising from low to high, you can see that there is a point, the time difference, and this is our propagation delay in terms of rising. And of course, if you look at this, this is the point at which the signal has completely fall from the high to low, and the corresponding point for the output is this, and you can see that there is a gap between the input and the output, and this is our propagation delay. Now for us to get the average value, we add the one during rising and the one during falling, and we divide by 2 to give us our propagation delay. Then the special property number 5 when selecting a logic gate is called the noise margin. The noise margin is nothing but unwanted, the amount of unwanted signals it can tolerate from other circuit when it is operating. And we have two sources of these unwanted signals. We can have DC noise and we can have AC noise. Where do we obtain the DC noise? We obtain the DC noise in the drifts, in the voltage levels of the signal. When you use an AC signal, pass it through a transformer, a rectifier, through a filter, and then finally through a regulator, all we are doing is to make sure that the output voltage remains constant regardless to the variation in the input or to the current demand. So any shift, any variation from the required value is called a DC noise in the signal. And then where do we obtain the AC noise from? We obtain it from a switching signals. That is, whenever you are turning on the system or turning off, it does not go on completely without any fluctuation. That fluctuation creates AC noise. And also when you're switching it off, the same thing. So the noise margin of any gate is defined as the maximum noise it can tolerate. Maximum. If you exceed that, it can malfunction, and we represent it in volts. So after seeing these families of logic gates and their special properties, the next thing we should look at is combinational logic. In digital electronics, we have two types of logic. We have combinational logic and we have what we call sequential logic. The combinational logic is given by this block diagram, and it is a kind of logic where your output at a particular time depends on only one thing, and that thing is the present input, meaning the inputs here are the determinants of the output. So we can now say that this output does, or this kind of a logic circuit does not have a memory, because it doesn't, or it does not store the previous output because we don't need it. And also it don't have any feedback because we don't need feedback to determine what should be the next output. It depends only on the present input. And as we know, the digital system works with binary. So whenever you have a combinational logic with n inputs, your output can be 2 raised to power n because we are using base 2 binary. So having seen this, we are now going to look at the stages or the steps you should follow if you want to design a combinational logic. The step number 1 is to state clearly the problem you want to solve. Then number 2 is to determine from that stated problem what are your inputs and what are your output variables. After doing that, step number 3 is to assign letters or symbols to your input and the output you have determined on this step number 2. Then step number 4, you use those information given to you to drive your truth table from the stated problem and go to step number 5, which is obtaining the Boolean function by simplifying what you have from the truth table. And after simplifying, you now use that simplified Boolean function to draw your logic diagram of the function. And let us take typical example to illustrate this. The example says design a combinational, this is supposed to be a combinational circuit with 3 inputs and 1 output. The output is logic 1, that is high when the binary value of the input is less than 3, and the output is logic low 0, otherwise that is when you have 3 and above. Now this is the first step, stating the problem clearly. Step number 2 is to use this problem to identify what are our inputs and what are the outputs. If you look at this one, we are told that we have 3 inputs and we have only 1 output. So having seen this, we'll now come and assign letters. Maybe this our 3 input, we call them A, B and C, and this 1 output we call it like F. So the next thing is to use that information to draw our truth table, and I have my inputs A, B and C and my output F. So for these 3 variables, the combination should be 0, 0, 0, 0, 0, 1, 0, 1, 0 up to 1, 1, 1. Everybody is expected to remember how to draw this kind of table. Now we create another column to give us the decimal equivalent. This 0, 0, 0 is equivalent to 0 in decimal, 0, 0, 1 is equivalent to 1, 0, 1, 0 is equivalent to 2, 0, 1, 1 is equivalent to 3, up to 1, 1, 1, which is equivalent to 7. And if we go back to our statement of the problem, we are told that whenever the input is less than 3, that is when it is 0, 1 or 2, these are the only ones that are less than 3, our output should be high. So at this point my F is 1, and this point my F is 1, and this point my F is 1, because all of them are less than 3. Now from 3 up to 7, they exceeded that value given to us, and therefore all of them should be logic 0. So we now state our problem, identify 3 inputs and 1 output, we give them letters A, B, C and F, and then we now draw our truth table. Now we should use this truth table to obtain our Boolean function using Kano map simplification. And if you can remember, we only consider those values of F where we have ones. So here I have 1 when my combination is 0, 0, 0, and here I have 1 when I have 0, 0, 1, here I have 1 when I have 0, 1, 0. So using these 3 values, I come and draw my Kano map. As I told you, you are expected to remember all this. Now my AB here, my C is here. If I wish, I can put A here, BC, I can draw it anyway, the value remains, and the answer remains the same. Now I have 0, 0, 0, 1, 1, 1 and 1, 0, then here should be 0 and 1. Now as you can see from this my truth table, the first place where I have 1, I have 0, 0, 0, which is this. The second place where I have 1, I have 0, 0, 1, and which is this. And the last place where I have 1 is 0, 1, 0, which is this 0, 1, 0. So I can combine these 2 adjacent squares and these 2 adjacent squares. If you look at moving from here to here, you can see that the value of A remains 0 and 0, but the value of B has changed from 0 to 1. So the one that has changed, we throw it away. And from here to here, they are all under C, 0. Therefore I have A, which is 0, 0, and C, which is 0, 0. So the simplified function for these 2 is equal to A prime, C prime, because of the zeros. And if you look at these 2, you can see that moving from here to here, the values of A and B remains 0, 0. But from here to here, the value of C has changed from 0 to 1. So C is discarded. I am left with A prime, B prime, because they are all 0, 0. Now, this is my simplified Boolean function from the Kano map. The last thing is to come and use this Boolean function to draw my logic diagram. And as you can see, I have A, B, and C, but all of them are prime. So this is my A, this is my B, this is my C. I pass all of them through an inverter so that I can have A prime, B prime, C prime. After doing that, I'll now come and say, here I have a product of A prime and B prime, which means I need an AND gate. So this is my AND gate. I'll input A prime and what? B prime to solve for this product term. The second AND gate should be for A prime, C prime. So therefore, this is my A prime coming here, and this is my C prime coming here. Now, after I produce A prime, B prime, and A prime, C prime, I will now look at the operation between them, which is a plus. So I use OR gates, and finally my output. This is how to solve this problem. If you look at it, we follow all the 6 steps given to us. The problem was stated. We identify 3 inputs and 1 output. We assign ABC for the input and F for the output. We draw the truth table. We simplify using Kano math, and finally draw the logic diagram. Now, the next thing is code conversion. This code conversion is also application of combinational logic technique, and it is used for designing a logic circuit that can be used to convert binary numbers from one coding system to another. The basic logic, coding systems we have in binary, we have BCD, which is binary coded decimal for coding 0 to 9. Then we have XS3 codes, we have 8421 codes, and we have 2421 codes. Now, if we want to design a code converter, the first thing that is expected of us is that we should be given the input code and the output code. You are not expected to cram anything. Then if those codes are given, we now represent them in form of truth table, and each one of them does the input code and the output. They should be represented with what? Latest. So now the next thing I will do is to come and find the Boolean function of each of the output variable in terms of the input variables. Then after doing that, I now come and draw my logic diagram after simplification. So for us to understand what I'm saying, let us take a typical example. We are asked to design a combinational logic circuit to convert BCD coded digits to 2421 coded digits. Now, as I told you, we will be given the input signal, which is said to be BCD here, and the output signal, which is 2421 coding. And now, what I was saying is this: my input are represented by A, B, C, and D, and the output are represented by P, R, S, and T. Now, what I will do is to find the Boolean expression for P in terms of A, B, C, and D, the Boolean expression for R in terms of A, B, C, and D, the Boolean expression for S and T, all of them in terms of this. And how do I do that? I'll come to P first of all and say, okay, under P, where are the places? I have 1 here, 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 and here, 5 of them. And what I will do is to go and draw a Kano math for finding the Boolean expression for P using A, B, C, and D as my inputs. Now, the first place I have 1 is 0, 1, 0, 1. The second place is 0, 1, 1, 0. The next place is 0, 1, 1, 1. The next is 1, 0, 0, 0. The last one is 1, 0, 0, 1. Now, I'll go and draw my Kano math. See it here, AB here, and CD here. I have 0, 0, 0, 1, 1, 1, and 1, 0, the same thing here. Now, I'll come to these places. The first one, I have 0, 1, 0, 1, and put it. This is where AB is 0, 1. This is where CD is 0, 1. Then I put 1 in the intersecting square. I put the second one, the third one, the fourth, all of them. Now after doing that, I can say these two are adjacent squares, these two are adjacent, then I can combine this one with this. So if you simplify this, as I told you, we are not expected to start learning Kano math in this class. They are supposed to be learned in 307. Now combining these two, I obtain their simplified function here. Combining the other two, I get their simplified expression here. And finally these two, this is their simplified. So this is P. My P is now equal to A prime BD plus A prime BC plus A B prime C prime. I do the same thing for R, I do the same thing for S, and I do the same thing for T. After doing that, you can see that here I have 3 terms, product terms. Here I have 3 also. Here I have 3 also, and here I have 2. So the first thing I will do here is to look at this and this and say, okay, is there any product term that is common like this? A prime BD, I don't have it here. But look at this, A prime BC, exactly I have it here. So A B prime C prime, I also have it here. So what we are saying is that since these two are common, I can cancel this and say, okay, now I have 1 2 3 plus 1 here, because these ones are repeated, I should not count them. Then I'll come to this one and say, okay, does it have anything in common with this or this? Yes, if you look at here, we have A B prime C prime, which is this last term. So since it is already obtained here, we also cancel it. So I can say I have 3 here plus 1 here, then I have 2 here because one of them is cancelled. So 3 plus 1 4 plus 2 6, and then these two, they don't have any as similar in any expression here. So I can say my product terms include 1 2 3 4 5 6 7 and 8. So I have 8 product terms. Now I'll go to the level of drawing my logic diagram of the converter. You know, we have 4 inputs, A, B, C and D. What I will do is to say this is my A, draw a vertical line going downwards, then tap from A, pass it through an inverter, pass it to the vertically downwards. From this inverter we have A prime, and from here we have the real A. You do the same thing for B, the same thing for C, the same thing for D, each one with its real and the prime. Now as I have shown here, we have 8 product terms after eliminating the repeated ones. Now I'll come and draw 8 and get 1 2 3 4 5 6 7 8, and I'll draw horizontal lines crossing these vertical ones. Okay, so after that I will draw the output also horizontally extending this way. Then after that I'll go back to my expression here and say how many Boolean functions do I have? P, R, S and T. So I will say, okay, since I have 4 of them, I will draw 4 OR gates here, and I will draw their lines vertically downwards crossing these lines. Then after doing all this, I will say, okay, this AND gate should represent this product term. What is it? A prime BD. I'll now come here and say, since this one is to represent A prime BD, where I have A prime, I'll put this dot to show connection. Where I have B, I'll put this dot. Where I have this D, I should put dot. So it means A prime enters, B enters and D enters, therefore this is my output. The second one, if you look at it here, is A prime BC, and I'll come here and say this A prime, this is B and this is C.